Hi and Assalamualaikum. So today we will be presenting our lab report on experiment 6, which is torsion of bar. Our group members consist of 4 people, which are Adeline, Raihan, Nakai, and myself, Faisal. So first we will go through the introduction. Torsion is the action of twisting, or the state of being twisted, especially of one end of an object relative to the other, while a force that tends to cause rotation is called torque. Torsion tests involve twisting a solid or hollow cylindrical specimen and measuring the resulting deformation as the angle through which the bar is twisted. The test then consists of measuring the angle of twist theta at various torque increments t. Next, the objectives. First, to investigate the relationship between torque t and the angle of twist theta of a circular or rectangular cross-section bars. Second, to determine the modulus of rigidity g of materials. Next, we will move on to theory. So torsion was defined as a body moving along its own axis. The magnitude of the torque was related to the force F and the perpendicular distance or moment arm d. The moment or turning force increases as the strength of the moment arm increases. The material will allegedly be shear strain as a result of body twisting. The stronger a material's stiffness, the greater its modulus of rigidity. By bending the material, the modulus of stiffness may be determined. Some theories that are related to this experiment are torque, angle of twist, polar moment of inertia, shear modulus, shear strain, shear stress, and lastly, the warping of the cross section for rectangular bar.
So this is the experimental setup for this experiment. The experimental setup include torsion bar testing machine, testing rod, which include aluminum rod, steel rod, and nylon rod, loads, measuring tape, screwdriver, and hanger cord. Next, we move on to the methodology of this experiment. The aluminum rod was clamped in the position and the load hanger was aligned to the cord. The rotation scale and the pointer were placed 400 mm away from the fixed clamp and the pointer was set to 0 degree. The angle of twist for each rod was recorded for every 5 Newton loads until 4 Newton loads was reached. Step 1 until 3 were repeated with both nylon and steel rods. Next, the rotation scale and pointer were moved 200 millimeter away from the fixed clamp after removing the loads. The angle of each rod was then recorded also for every 5 Newton loads until 4 Newton loads was reached. These steps were also repeated for all the testing rods. Finally, the diameter for each rod were measured using vernier caliper and were recorded. We move on to the progression steps of this experiment. First, be careful when handling the heavy loads to avoid the loads dropping and causing injury. Record the angle of twist only when the load is not swinging. Make sure eyes are perpendicular to the reading scales to ensure accurate reading of results. Finally, make sure to carry out the experiment in a closed area to decrease the effect of wind towards the result.
Next, this is the data analysis for aluminum alloy rod. We managed to get the angle of twist for this rod, and the diameter for this aluminum alloy rod is 6.21 millimeter, and the radius is 3.105 millimeter. The second table shows the steel rod data, and the diameter is 4.91 millimeter and radius is 2.455 millimeter. So this is the last table for this experiment, which is nylon rod. We can see that nylon rod have the biggest angle twist among aluminum alloy rod and steel rod.
The graph show is the figure 6.4 shows the graph of torque versus angle of twist for aluminum alloy rod. Based on this graph, the M value can be retrieved from the graph for both length, which is for 400 millimeter is 0.00775 and for 200 millimeter is 0.0047. The value of M is the linear slope of the torque for both length. Next, figure 6.4 shows the graph of torque versus angle of twist for steel rod. Based on this graph, the M value can be retrieved from the graph for both lengths, which is for 400 millimeters is 0.0086 and for 200 millimeter 0.0041. The value of M is the linear slope of the torque for both lengths. And next, figure 6.43 shows the graph of torque versus angle of twist for nylon rod. Based on this graph, the M value can be retrieved from the graph for both lengths. For 400 millimeter, it's equal to 0.0603, and for 200 millimeters is 0.0325. The value of M is the linear slope of the torque for both lengths.
Next, this is the formula to calculate torque and modulus of rigidity G. First, torque, the given formula is T equal to Fr sine theta, where R equal to radius of the rod, F equal to magnitude of force applied to the load, and theta is angle between radius and force. Then G, modulus of rigidity, G equal to TL over G theta. Then L equal to mj, where polar moment of inertia J equal to pi c power of 4 over 2, m equal to value of slope from graph, T over theta, and is length of the rod. After we have done calculate the torque by using the formula torque equal to Fr sine theta, next we need to calculate the modulus of rigidity G. Uh, For the aluminum alloy rod, the radius is 3.105 millimeter, and from the graph we can get M for 400 mm away. The M value is 0.00775, and for 200 millimeter away, the M value is 0.0047. Next we need to calculate the polar moment of inertia J, and then the formula is pi c to the power of 4 over 2, and we get 1.146 millimeter power of 4. For L, for the length of rod, which is 400 mm, the modulus of rigidity is 20254.80 Newton per millimeter square. And for length of rod, which is 200 millimeter, the modulus of rigidity is 16699.44 Newton per millimeter square. Next, we need to calculate the average modulus of rigidity, and we will get 18477.12 Newton per millimeter square. Next, we need to calculate for steel rod and nylon rod using the same operation and same formula.
And for this discussion, three graphs which shown in figure 6.41, 6.42 and 6.43 has been plotted show the relationship between angle of twist against torque for aluminium, steel and nylon. The graph shown linear trends with the increase of load applied. Based on the graph, we know that the twist angle is keep increasing, even the increment of the torque is very small. Based on graph, for steel it shows the biggest change in the twist angle compared to aluminum and nylon, even the same increment on torque applied. Next, steel has the highest modulus of stiffness G on the graph, followed by aluminum and nylon has the lowest modulus of rigidity. While nylon is non-metallic substance, steel is extremely strong and stiff, while aluminum is lightweight and resistant to corrosion. When compared to nylon and aluminum, steel will exhibit the largest difference in rotational length. This is because steel is a brittle material that, in the absence of torque, reverts to its original form, while nylon is a non-metallic substance with extremely strong properties. Aluminum is a ductile material. Furthermore, the modulus of stiffness was influenced by the kind of material. The ratio of shear stress to shear strain in a structural bar is known as the modulus of rigidity, or shear modulus. Therefore, the higher the modulus of stiffness, the more elastic the bar. The applied torque is directly proportional to the bar's twist angle. The bar's twist angle is directly proportionate to its length. As the bar's diameter grows, the twist angle of the bar lowers. It is directly proportional to the bar's form for the polar moment of inertia. The polar moment of inertia grows in proportion to the bar's diameter. The polar moment of inertia also increases proportionally with the modulus of rigidity. Lastly, for the conclusion, the experiment's goals were to find the maximum shear stress and shear strain as well as the relationship between torque and twist angle, as well as the material's modulus of rigidity. It is evident from the displayed graph that for the three different materials we utilized, torque was directly related to twist angle. Regarding the modulus of stiffness, G, the computation section indicated that steel had the greatest average G value, followed by nylon and aluminum, while nylon has the low shear modulus value, which indicates that it is soft or flexible. Steel has a high modulus of rigidity, meaning that it will hold its shape and require a big force to deform. Because we did not employ enough load to accomplish the maximum angle of twist, we were unable to determine the maximum shear stress and shear strain based on our experiment. As such, we were unable to compute it. The experiment did, however, allow us to determine the percentage of inaccuracy between the experimental and theoretical values. Aluminum and steel have smaller percentage errors than nylon. Thank you.